Welcome to the webinar on hybrid cloud for IoT. I am Gaurav Makkar, a technical director in the Advanced Technology Group at NetApp. NetApp is a Fortune 500 company specializing in data management and storage solutions for enterprises. I would like to thank HackerEarth for hosting this webinar, and let's get started. You'll see shortly that this webinar actually goes much beyond the title of this presentation. I would have rather called it "What Should Programmers Care About in a Couple of Years?" And while a lot of change is being driven by technology shifts, business momentum around IoT and real-time analytics are huge contributory factors that we'll actually see. I will breeze through the initial slides as they cover some background material around IoT. But fundamentally, I would like to get into the fast data in IoT and the impact of media trends in this world. We tend to hear and attribute a lot about IoT to connected cars and wearables. But when you consider where money is being made, most of the money is actually being made in IoT is in the enterprise. And it is about solving problems in the context of the business of that enterprise. Predictive maintenance is considered as that killer app for IoT in the enterprise space. Typically, when a machine fails, it not just brings the related part of the business to a grinding halt, it may also affect its environment in a manner that might not be conducive. For example, an accident on the shop floor of a manufacturing unit does not impact only the failing machine, but also may put the neighboring machines at risk. Thus, it is critical for businesses to predict when a machine should be taken out of service for maintenance. Analytics is at the heart of any IoT process, and questions are the seeds from where this journey starts. In the context of predictive maintenance, here are some example questions that are typically asked in different verticals. All these questions fundamentally asking the same question really, which is, when should I service the machinery so that I minimize service downtime, minimize business risk, and minimize costs associated with operating the business. And in order to be able to do or be able to predict something, we must know the variables that contribute to that cause. There may be hundreds of sensors in a business process, but we need to have mechanisms to identify which ones contribute and impact an output variable of interest. And for a different output variable, the set of sensors that we choose probably would be very different. We would also need to know how these variables are correlated. This correlation may be expressed as a series of arbitrary complex system of equations, as an example. Further, we would need to know what is normal versus what is an anomaly. The promise is that having trained the system, that is the promise of analytics, is that having trained the system using historical data, one should be able to reasonably predict what might happen in the near future. But a lot of the prediction capability will depend on the quality of the data being collected and the efficacy of the model used to represent the system. This is one such simplified way of arriving at whether an event is likely in the near future or not. And then a related question is, how far is that possibility? Anyway, all those questions are in the realm of analysis that is done on data collected from sensors. But not all data that is collected is analyzed in probably the same way. In some cases, the collected data is organized and transformed so that it may be presented through rich visualizations. For a trained eye to spot the anomalies. It is not uncommon in the oil and gas vertical, as an example, to see this workflow. In this visualization that you have on the screen, the flow of oil and gas is being charted. It is for these highly intricate visualizations that we see niche GPU-based databases like Kinetica DB being used. But all this data analysis and rendering must happen in real time, or more accurately stated, in machine time. In traditional data analysis, most of the insights and reports produced were consumed by humans and in human time. Producing a summarized report every minute is not going to be terribly useful if a human at the other end of that workflow is examining it manually. But as we automate processes and add algorithmic intelligence into the workflow, a computer can replace the human at the other end. It may even suggest changes to the system parameters that can help bring the system to normalcy or help guide it. As the confidence on these intelligent systems increase, it should not be surprising to expect response times to further reduce as the human-centric bottlenecks are eliminated. A beautiful manifestation of this maturity is the emergence of chatbots for technical support. But all this processing, analysis, and response really starts with data collection. What I have drawn here is a modified form of a Lambda architecture, and I wanted to bring the notion of a model front and center. To briefly describe what is happening here, I've taken the data flow of a single sensor that is being split at this point and is being sent to the compliance engine on one hand and a form of a data lake at the other. The compliance engine checks for anomalies and fabricates a response using help from the model and responds in real time. A model can be considered as a set of rules or a set of constraints and can be arbitrarily complex. The amount of data accessed and processed during this path is very small during this path. On the other hand, when the model updater kicks in, let's say once every 8 hours, it has, so this is the model updater, when that kicks in, it has a much larger amount of data to work with to refine the model. So that's the model in question. How often this batch update is needed is very specific to the needs of the business. As data gets colder, its immediate relevance reduces, but it might still be needed for provenance and troubleshooting purposes. So fundamentally saying it's not thrown away. It is also useful to retain data sets to train and refine the algorithms. This data corpus builds up over a period of time and needs to be managed differently from the hot data in active use. Effective management of this data lifecycle has a significant impact on the cost of the solution. On the other hand, if data is not available to be served when needed, the expected service level is impacted. So both cost and service level are two sides of the same coin. This is where the cloud comes into the picture. IoT workflows are about meeting SLAs under tight cost controls. Cloud provides a very effective storage tier for cold data management through solutions like S3. In some cases, it might be prudent to directly ingest data into the cloud, and low latency persistence solutions in the cloud can be leveraged. The exact combination of this hybrid cloud deployment depends on the source of sensors, that is the location of source of sensors, and the nature of SLAs. It's hard to generalize where data will be ingested first and when it should be moved. The one thing that did not work in the favor of cloud in the past had been that IoT front-end workflows almost always needed to be working 24/7. They're always up and running. The cloud infrastructure in the past had been built on the assumption of low utilization of resources by any single process or person. They heavily virtualized. To support the event-driven nature of IoT, cloud infrastructure had to respond by reducing the unit of compute resource to be much smaller than a virtual machine. This is where solutions like containers enabled by Docker help to form the basis of the event-driven nature and workflows of IoT. More often, we see IoT data being collected in the enterprise and then moved to the cloud as it cools off for batch processing or cold data archival. But because large amounts of data are difficult to move around, we have seen cases where data archival is kept within the enterprise. Through these examples, I'm basically trying to come to the conclusion or say that the exact deployment model of the hybrid cloud for IoT is very specific to the constraints and needs of a business. I would like to now switch gears into the data needs of IoT solutions and the technology trends influencing those solutions. The basic data needs in IoT fall into three, what I would call data islands. The first data island is the low latency tier, where data lands in from various sensor devices. This is also the place where decisions are taken in machine time and response is generated to control one or more sensors on the field. The amount of data that is used in this tier might run into a few terabytes. On the figure, the left side of the graph so the left side over here provides coverage with flash and storage class memory based solutions. So briefly about, so we have SCM over here, very briefly about what storage class memory is. That these are media devices that provide byte granular access by providing persistence. So it's like memory, but with persistence, and therefore are more generically also termed as persistent memory solutions. And SCM, if you notice, plays directly into the memory gap or the memory hierarchy gap of DRAM and flash. The second data island is the slow data island, and in more storage-centric parlance, it is also called the active archive. This is also called the data lake in some marketing literatures. Raw data from multiple sources, not just sensors, is placed into this large data repository. From an IoT standpoint, refinement of the data model happens from data that is present here. For example, the conditioning of windmill parameters can be affected by a prediction of an impending strong wind condition by the weatherman. So that data is not streamed in through sensors, but is available through offline means and out-of-band means into the data lake. Thus, the amount and variety of data in this data repository lends itself to complex analytical processing. NetApp provides storage solutions in this space through our flagship product, ONTAP, or even SolidFire, as the case might be. Most of the capacity flash-based solutions operate in this space. So these are the capacity flash solutions over here, which is TLC, and you even have quad layer solutions that are coming very soon. The third data island is typically not even seen in books, and for that reason I just called it the dead data island. This is really the cold archive. Data is rarely extracted or accessed from these repositories. Data is maintained for compliance reasons, and for your mental model, think of this as being the Amazon glacier tier, which is below the S3 tier in the Amazon world. NetApp provides solutions in the space with storage grid web scale. The solutions with cloud and archive drives that you have on the figure over here operate in this solution space. Having laid the landscape of data solutions needed in the IoT space, I would like to focus only on the fast data island for the purposes of this webinar. The figure here shows a plethora of media options available to build the right storage solution for one's needs. For fast data island, one needs to focus on the flash and storage class memory tiers towards the left of this figure. If the infrastructure can hide all those nuances of media options and present simplified APIs that an application programmer can use, that will be the most effective solution. In fact, that is what is expected of data solutions. And in the past, this concept has played out well. Inefficiencies and high latencies in the software data paths typically did not need to be optimized because the media was not fast enough to expose those inefficiencies. Bottlenecks were really in the access from disks. The situation is changing very quickly. Infrastructure bottlenecks are being eliminated, and the bottlenecks are now shifting into the application space. This is why we can't just say it's an infrastructure problem. Unless the applications themselves are privy to this change, the data solutions that are built by the applications will land up being inefficient and very expensive. The analogy that I would like to drive here is very similar to solving traffic congestion problems. Building a flyover or an overhead bridge eliminates congestion at that point, but shifts bottlenecks elsewhere in the chain. I will try to present some under the hood happenings because very soon applications will need to change and programmers will need to be aware of those nuances. So please do not write off these shifts as infrastructural only. Apart from the cost parity being achieved between compute and media, the media will soon be fast enough such that the access to it will not be block oriented and will need to be synchronous. That is the singularity that we should look out for, but it'll take towards the end of the decade to play out. And a lot of work needs to be done even before that hits us. But then, if we choose to ignore these shifts due to technology, our applications will probably fall into the problems seen by legacy applications, where contention in the application is so high that only about 10% of the CPU was being spent in doing useful data processing work. And these issues get more pronounced as latencies of media are reduced and the number of simultaneous threads increase. I will touch upon this more in a couple of slides, but I would urge you to read the seminal paper by Michael Stonebreaker, who showed why a radical redesign and rethink was needed in the database. a lot of the columnar DB concepts that we see realized today also stemmed from that and related work. So back to the architectural components of the fast data island. Kafka is a key orchestrator in the fast data island. It has the notion of topics into which it logically segments, or actually the programmer could logically segment incoming data. It can filter and do basic transformations of data before giving or handing off that data downstream. It follows a publish-subscribe model, and processing and storage elements downstream can subscribe to a data feed at a certain rate. This architectural paradigm, which came from multiple years of work in LinkedIn, has become the de facto data pipeline orchestrator for the IoT data pipeline. Spark is one of the downstream subscribers that handles the responses in real time. But Cassandra is where data gets persisted. Typical deployments of Cassandra are clusters of nodes having some direct attached storage, like a disk or an SSD with it. So each green blob that you see in the Cassandra cluster here is a compute node that also has locally attached storage. How Cassandra handles incoming data, protects data, and lays it out on media are critical design decisions for maintaining high resiliency and for maintaining high levels of concurrency. Incoming data is written to memory and logged in the write-ahead log. This is to enable recovery through log replay, which is a typical Aries-style recovery model. Cassandra then asynchronously writes out the chunk of memory onto persistent media and calls that a sorted string table or just SS table. It is called that because the contents of an SS table are sorted strings consisting of key value pairs, basically sorting on the key, associating the value with it. Multiple SS tables are later combined and merge sorted. And in the merge sort process, older data which got overwritten logically could then be eliminated. But data is never overwritten physically. That's the fundamental aspect of log structured merge tree, or just LSM. Almost all NoSQL databases essentially have an LSM structure through which they manage persistence. Thus, Cassandra never writes data in place. This design decision implies that Cassandra is very good with multiple threads and has high concurrency, as there are never any read-write conflicts on persisted data. But with the introduction of Flash, here is where I talked about this introduction because I wanted to get to the point of changes and inflections. Because with the introduction of Flash, the transaction throughput is improved due to the lowered data path latency. This is achieved by placing the write-ahead log, which is really in the data path, on Flash. But because the SS tables are also placed on Flash, that creates a problem with Flash endurance, as write amplification is increased due to the log structured merge tree operation. Remember I said at some good point in time, a number of these SS tables are taken and they are merged, sorted, and then the resultant is also written back onto Flash. So therefore, for every write, basically I double the amount of writes. So the write amplification just increased. So while unmodified Cassandra would do well by just moving to flash, the flash would wear out much quicker, needing to replace that much sooner, thus impacting cost of the solution. Essentially what I'm trying to say is that you cannot ignore the cost of the solution. Design decisions directly impact the cost. As engineers, that aspect has to be front and center. Furthermore, Cassandra was built, optimized for the disk world originally. When operating with disks, a random seek to media is of the order of 10 milliseconds, which was very high. If we would have to entail multiple such random accesses to serve a single query on a Cassandra key space, let's say you were doing a rain scan and you basically said, okay, fine, let me find out where all this key is actually available on disk and on storage. I really have to look up probably multiple of these SS tables and then throw away those SS tables because the key did not actually belong to or was not available in that SS table. So instead of doing that, because if you did that, no way you could actually provide a solution or a read or a rain scan in deterministic time. The goals are not just about lowering the latency of operations, it's about being deterministic. The solution should be deterministic. So in order to eliminate the spurious requests to random locations on disks, Cassandra employed Bloom filters. It looked up the Bloom filter to determine if the key being accessed is in that location on disk. If the Bloom filter said yes, then there was a high probability that the key is in that data block and a disk read is issued. By adopting this mechanism, Cassandra eliminated most spurious disk reads. When simulating Cassandra on fast media, and that is what this chart is about, these Bloom filters tend to hold back Cassandra. You have this is a split of the latencies and where time is being spent. This is where in the disk-oriented world, that SS table scan by the Bloom filters was actually happening. So again, in order to eliminate the spurious requests to random locations of disks, the Bloom filters were adopted. So when simulating Cassandra on fast media, these Bloom filters tend to impede the performance of Cassandra. The Bloom filter subsystem that held Cassandra perform extremely well with disks turned out to be an impediment when moving towards low latency media. This is shown in the magenta section on the latency breakup charts and how this increases. This simple exercise was to prove a point that applications will need to change when moving over from a high media latency world to low latency ones. The architectures, data structures, and approaches will probably need to be rethought. Another observation that came out of this exercise was a revelation that the age-old software architecture technique of building high-load server systems, called the staged event-driven architecture, also called the SADA model, starts to break down with low latency media. By the way, the SADA model is almost a 20-year-old technique. The SADA model relies extensively on queuing and scheduling across stages of processing within an application. In the era of low latency, this queuing and subsequent scheduling increases the latency and kills latency right there. Thus, architectural paradigms that have been in use for the last couple of decades will now need to be rethought and redesigned. And that was just traditional flash, which operates at about 500 microsecond latency. NVMe flash which operates at about 100 microsecond latency, is now available. And soon, Intel plans to launch 3D XPoint based NVMe devices with latencies close to 10 microseconds. Over the last couple of years, significant work has been going on in the Linux I/O stack to prepare for such media and eliminate software latencies and contentions. Linux has been made NVMe ready since version 3.4, and that's quite some time back, by the way. I quoted the examples from Cassandra and Linux primarily because most applications consider Linux as the infrastructure provider and the database as the persistence provider. The fact that both these elements have been changing and aligning to low latency needs, the onus will soon shift to the application to start considering the impact of low latency media. To put the impact of this shift in context, a single NVMe device in the near future will support close to 1 million IOPS. And compare that with the 200 odd IOPS that we got from the best of disks in the past. It was also not uncommon in the past to have about 4 disks per node in a Cassandra cluster. It will be almost impossible for a single node to saturate those devices when they are directly attached to the nodes. That would be leaving performance headroom on the table for those expensive devices, and that will only increase the cost of the solution. Thus, it is imperative that the deployment model, again, be rethought. So RDMA, this is a classic example of not every technology sees the light of day immediately, but RDMA was first introduced actually more than 12 years back. This year, finally, 2016, might well be called the year of RDMA. This allows, that is RDMA, allows for doing direct memory access to a remote node without intervention of the target CPU. The promise of RDMA is that the performance of a rack local media access, which will hop over the rack's backplane network, is very similar in performance, very similar to node local access. Thus, the media could be consolidated. Well, you need not have the media in every node out there. If that's the case, I could actually go consolidate all media into top of rack, as shown in the diagram and the figure on the left side, and shared across multiple servers in the rack. This also helps fully utilize the performance potential of these devices. The figure on the left shows the consolidation of persistent storage top of rack, with accesses from server to top of rack flash being made possible through NVMe over RDMA over Ethernet. So 20 years back, shared storage was created because the IOPS from a single device was not large enough. Like I said, 200 IOPS from a single disk. By aggregating sufficient disks together, the aggregate throughput could be improved. We again have the need for shared storage. The reasons might be very different, but the need for shared storage is rising, and the technology building blocks are in place to allow for that to be real. Over the last decade, we've gone from shared storage to distributed shared nothing architectures, and again contemplating the need for shared storage. I quote this example because solution architectures need to be re-examined and preconceived paradigms might not apply. Incidentally, NVMe over Fabric support was added to Linux 4.4. If I've not gotten it wrong, I think July this year. So there are two graphs over here. The top graph in the center of the slide shows that the local performance closely matches remote access performance when RDMA is leveraged. And the bottom graph shows the same on the latency dimension. There is more work to be done in this. This is, just starting to pan out. So what's next? So has the infrastructure stabilized enough, and can we start discovering new paradigms around it? Like I said, a lot of these software architecture and paradigms need to be examined. But the mother of all changes is frankly yet to come. This change happens when the main memory inside each node becomes persistent. This movement is already underway with more than 8 vendors providing NVDIMMs, non-volatile DIMMs, which basically are memory modules with some flash on them. So if you see this figure, you have the DRAM, traditional DRAM, and you basically have some amount of flash on this, and you have the NVDIMM controller here. On detecting power failure, the ultracapacitor, which is the green thing over here, attached to the NVDIMM holds enough charge to enable the NVDIMM controller to flush the contents of the DRAM into onboard flash. When power is restored to the node, contents of memory are repopulated from the onboard flash. I've glossed over a lot of nuance and details that actually happens behind the scenes to enable this operation. But these devices are market ready. They're starting to be leveraged in commercial software like 2016 release of Microsoft SQL Server. But then we just consolidated persistence. Last slide we just talked about this. We just consolidated persistence into top-of-rack solution and access the same over RDMA. So why ping pong? Why not just wait till this becomes a reality? So this is because the NVDIMM model, by the way, can be very disruptive to applications, much more than what we are seeing today, if used in its native form. So NVDIMMs will redefine the notions of persistence and storage. And when all issues are deemed resolved, one could see application data structures being persisted natively. Actually, if you wanted to go see some work that is happening in this space, it would be great to take a look at a website called pmem.io if you're interested. So 4K based block IO will probably not make sense if you start to persist data structures in a consistent way. But block IO will probably be only needed for legacy application support. Persistence will be focused more on cache line sized load store operations directly by the application. Imagine storing a cache or flushing out a cache line into persistent memory. Basically sticks that data in there. Even if there's a power loss, it just stays. This is the sweet spot, by the way. Even the size that we just talked about is in the sweet spot of sizes of sensor data, most of which is really just about 100 bytes, or actually less. But that model will take some time to become pervasive. To address the question, will deployments have node local persistence or rack local persistence? The answer is that, or at least our assessment is that, both have their merits and both models will be prevalent. Both technical and deployment preferences will influence that decision. It's not just a technical decision. So in closing, I would say that it's a great time to be innovating in the infrastructure space and application space as a result. There's a lot changing, and long-held beliefs are being challenged and changed. Very significant innovation potential exists, and the timing is also perfect because business needs from fast-growing sectors like IoT are driving the need for resilience. If the need for a technology naturally is not established, it just languishes, like actually RDMA did for so many years. But that is not the case here. And one should expect this to only increase as the pace of business aligns to operate in machine time. I would expect these technologies to appear in the cloud as cloud provides the volumes for a technology to be mainstreamed. The next few years through the end of the decade will see the face of software and architectures being redefined. Thank you for your time and listening in. I'll be happy to take questions now. I guess there is the questions tab on the right side that you can actually go place a question in. Let me know if there are any questions. I'll hold off for a couple of minutes. If there are no questions, we'll sign off. Okay, so thank you very much. I would like to thank the participants for the time and Hacker Earth, the organizers, for putting this together. We can end the session now. Thank you. Bye-bye.